Welcome, everyone. On behalf of Dallas College and the sustainability team, my name is Faye Davis, and I'm joined by my team members Sonia Ford and Lori Dela Cruz Lewis, who are both working in the background. We are also grateful for the support of our Dallas College WebEx support team. So without further ado, I'd like to introduce your speaker. Welcome back, Dan Moulton. Dan Moulton is a wildlife ecologist with a BA in biology, a master's in wildlife ecology, and a PhD in wildlife science. He is recognized as a certified wildlife biologist by the Wildlife Society. He has worked for the U.S. Fish and Wildlife Service in Hawaii and Maryland, the Maryland Wildlife Administration in Annapolis, and for over 20 years at the Texas Parks and Wildlife Department in Austin. After retirement from TPWD, he taught for over 6 years as an adjunct professor of environmental science and biology at several colleges in the Dallas area. He presently serves as the executive committee chair of the Dallas Sierra Club. Thank you for joining us again. Mr. Moulton, please get started.
Okay, good afternoon, everyone. This talk is about nuclear energy, not nuclear, but nuclear. And the reason we're interested now in nuclear energy is that we hope it will help us to get off of fossil fuels and make the transition to renewables. So this picture here shows a nuclear power plant in Salem, New Jersey. If you'll notice, these three domed structures are the nuclear reactors. So this plant has 3 reactors. This big tower over here with the steam coming out is a cooling tower, because what these produce is very, very superheated water, and they have to cool it down either by using a cooling tower or putting it out into this natural body of water. About 30% of New Jersey's electricity comes from nuclear power. Introduction to the nuclear process. There's 2 things we're interested in: nuclear fission, which is what happens when you split atoms. This is what happens in most nuclear plants today, and also the earlier atomic bombs. Fusion is what happens in the sun. Nuclear energy is released when atoms fuse together to produce different elements, and energy, lots of energy, is released. Briefly, let's take a look at atoms and see what we're talking about here. Atoms and radioactivity. Here is an atom of helium. I know that because it has 2 protons. It also has 2 neutrons and 2 electrons. The protons have a positive charge. The neutron has no charge. The electrons have negative charge. So the nucleus consists of the protons and the neutrons. And normally, the protons equal the neutrons equal the electrons. The atomic mass of an atom is the number of protons plus neutrons. So in this case, 4. The atomic number is the number of protons, in this case 2. It is the number of protons in an atom's nucleus that determines the identity of the element. So normally, as we said, protons equals electrons equals neutrons. Here is a schematic diagram of an oxygen atom. 8 protons, 8 neutrons, and 8 electrons. This is carbon. 6 protons, 6 neutrons, 6 electrons. And as you can see, the fact that the proton number is different gives us 2 different elements. Carbon. This is actually an isotope of carbon. If the number of neutrons in the nucleus exceeds the number of protons, then you have an isotope. This is still carbon because it has 6 protons, but it has 8 neutrons, so that makes it an isotope. And in this case, this is carbon-14, which you all know can be used to date organic materials from the past. The chemical behavior, which is controlled by the electrons in the electron shells, is identical to carbon-12, okay? But isotopes are often radioactive. that is, they give off radiation and particles. That's why carbon 14 can be used to date things, because as the carbon 14 gives off radiation, it turns back into carbon 12. So you can use those measurements about carbon 14 versus 12 to date things. Common radioactive isotopes. Okay. Common isotopes that are associated with the fission of uranium, such as happens in a nuclear plant. The half-life is the amount of time it takes for half of the radioactive atoms to break down into non-radioactive atoms. And you can see the half-lives of various radioisotopes vary by quite a bit. You can see why a plutonium bomb is called the dirty bomb. The half-life on here, we're talking about thousands and thousands of years for half of the material to break down. So in a situation like Chernobyl, which we'll talk about later, these areas will remain radioactive for a long, long, long time. What is the nuclear fuel cycle? Okay, well, we have to mine uranium and mill it, because naturally occurring uranium is U-238, and a very small fraction of it is U-235, and that's what we use in the nuclear reactor. So we have to enrich the U-238 to make more U-235. We only need like 5 to 8% to run a nuclear plant. There will be tailings from the mines and the mills. There will be depleted uranium tails from this enrichment process. Then we fabricate or put together the fuel assemblies that go into the reactors, and that produce factory wastes. The nuclear power plant, where the assemblies go, will give off low-level waste. Spent fuels are stored on site. We'll look at more of that later. That's where most of the stuff is now, at the plants where it was produced. But deep geological disposal is something that is not done much right now, but they're attempting to figure out how to do this. Spent fuel reprocessing, you can go back and make more U-235, et cetera, et cetera. So now let's just take a look at this simple diagram on what nuclear fission actually is. So there's a atom of uranium-235, which is what's used in the plant. As that is bombarded with a neutron coming in, what happens is the U-235 splits into two other atomic fragments, and it could be stuff like krypton and barium, various other elements. They'll be completely different elements, of course. Also, free neutrons are given off in this splitting, plus a lot of energy in the form mostly of heat. So then the free neutrons hit other U-235 atoms, and the same process goes on, and this is called a chain reaction. The free neutrons at this end on the right will hit more U-235, more neutrons will be given off, more heat energy. And this process is used to heat water to make electricity. And here's how it's done in your conventional nuclear power plant. Over on the left, here's this domed containment building that we looked at 3 of them at that Jersey plant. This is called the reactor vessel. Okay, so in here we have our uranium fuel assemblies, and also these control rods, which are made out of special metal alloys that are designed to capture free neutrons. This is the way that you can speed up or slow down the reaction process. Okay. Inside the reactor core, you have liquid water under high pressure. It's very, very hot. This heat goes to the steam generator. It heats this water up and makes steam under high pressure. The steam goes to a steam turbine, which spins the blades, turning the electric generator, producing electricity. Now, this hot water can come back through a condenser and come back to the heat exchanger to go around like this. Or if you need more cooling, the water will go to a cooling tower or some natural body of water, which means you'll have to pump more water. Sometimes the heat is so excessive that you need to cool it down before you can put it back into the heat exchanger. So it looks simple, doesn't it? We're not going to talk about breeder nuclear fission. Let's look at the locations of nuclear power plants in the United States today. There are 55 plants in 28 states. Now, 55 plants isn't the number of reactors, because the picture we saw at the beginning, that plant had 3 reactors, okay? And many of them, most of them have more than 1 reactor. As you can see from this map, most of the nuclear power plants in our country are in the eastern part of our country, mostly east of the Mississippi River. You will see that we have one here. This is the Comanche Peak plant near Glen Rose, Texas. The second active plant is the South Texas Nuclear Project, which is in Matagorda County near Bay City. And in the western U.S., there are now relatively few operating nuclear power plants. The first nuclear plant in the U.S. opened in 1958 in Shippingport, Pennsylvania. That's right down around here, you see. And then there wasn't a lot going on until we hit the late 70s, and then suddenly we started to make nuclear power plants. And this goes up to 2018. We'll go over to this little inset here, and you can see that this is the most electricity that's ever been made, was in 2018. You might find this dip here interesting. Something happened in 2011, right here, and it was the Fukushima meltdown in Japan. I'll talk about that a little bit later. So then some old plants that they weren't too sure about the safety of went out of operation. And then they slowly came back, and here's where we are basically now. Let's look at the pros and cons, some of them. Impacts on land use. Coal uses a lot of land, of course, to mine it primarily. Nuclear, much less. Daily fuel, coal uses 9,000 tons a day. 3 kilograms a day for nuclear. Air pollution is moderate to severe, and it's very low for nuclear. Radioactive emissions are, of course, practically nothing for coal, and a lot for nuclear. Catastrophic accidents, short-term local risks from, mishaps at coal plants, and a long-term risk over a large area if you have a serious mishap at a nuclear plant. More pros and cons. Is electricity produced by nuclear energy cheap? Well, it's about the same as other sources of energy. But the building of nuclear plants is a different story. They're very expensive to build, and government subsidies have been involved in that. The cost of building a nuclear power plant is high. Fixing technical and safety problems in existing plants is high, but not as high as building a new plant. So more about that later. Can nuclear energy decrease our reliance on foreign oil? Well, not really, but that's because we don't use oil to generate electricity in the United States. Only 3% of our electricity comes from oil. Oil is used mostly for heating buildings and running vehicles of various sorts. So let's look at electricity generation by energy sources as of last year. You can see that at this point, fossil fuels is producing over 60% of the electricity we use in America. And of that component, natural gas makes up the biggest component. Coal is significantly less, and petroleum, as I said, is practically nothing. Now, down below, it says nuclear is providing approximately 19% of the electricity we use in America, and that's a significant amount of electricity. Renewables are producing approximately the same at 20%. And most of that is coming from wind, which is a rapidly growing sector of the energy industry. Hydropower, 6%. And as of 2021, solar was at about 3%, but that is a rapidly expanding sector of our energy economy. Cost of electrical power plants, but this means these data are old, so I'll make a comment. This is generating costs of electric power plants. Okay, well, they're all pretty much the same. The one that sticks out is photovoltaics. That's solar panels such as we have on our roofs, you know, and that appears high, but these data are quite old, and this cost has been coming down very rapidly for the last 10 to 15 years. And this number now is going to be comparable to all of these other sources in terms of generating costs. This isn't the cost of building the power plant. Okay, it's the cost of generating electricity per kilowatt hour. This is an important graph because it makes predictions. Electricity generation and shares of total from selected fuels and renewable sources. And these data are from real data up to 2021 last year. And then they're making predictions on the right side of this line out to 2050. So let's look at this. Right now, natural gas is where most of our electricity is coming from. Here's the 21% for renewables. Nuclear is that 19%, and coal is at 23%. Now, what we want to do in the future is make this coal wedge smaller and smaller and smaller, and these bigger and bigger. And we'd like to decrease natural gas too. 44% renewables by 2050. Well, that's good. That's good progress. You can see that nuclear has stayed about the same in terms of kilowatts, and that's if no plants are brought back online. In other words, it isn't going to change. The share goes down, of course, out here. Coal is decreasing. That's great. That's what we want. Natural gas is not decreasing according to these predictions here. It's a slightly less share because these are increasing so much. Let's look at the renewable electricity generation. Here we are at that line, and what we're looking at here is this wedge here. You can see that solar is predicted to grow tremendously by the middle of this century, going from 19 to 51% of our total electric generation. Wind is also predicted to increase in terms of production of electricity, but the share goes down because this is increasing so much. Hydroelectric stays the same, basically. That's because the building of large dams is kind of a thing of the past. So this is good if it comes true. Let's now talk briefly about some of the obvious safety issues in regard to nuclear power plants. The probability of major accidents is quite low, but when they occur, the consequences are widespread, long-lasting, and very serious. Major accidents that we know about have included 3 Mile Island, which is in the Susquehanna River between Pennsylvania and New Jersey. That was in 1979. That was a serious situation where a meltdown almost occurred, but it didn't. Jimmy Carter was president at that time, and he, being a nuclear engineer himself, he went to the plant and went inside, which was pretty risky. But I don't know if he helped the situation or not. And then we have the one you all know about, Chernobyl, 1986. This picture on the right is the reactor at Chernobyl that melted down and exploded. Okay, and that's the most serious accident that has ever happened. But another one was Fukushima in Japan that was caused by the earthquake and the tidal wave that hit the plant, 2011. And you remember that dip in the nuclear power plants that were operating? It was right after this, because that was a serious situation also. And they're still trying to deal with it and contain the radioactivity. Let's look at what we now know happened in terms of radioactive fallout from the Chernobyl meltdown and explosion. The red is heavy radioactive fallout. The orange is medium. You can see that this wasn't a situation that was limited just to the Ukraine. And actually, Russia got off pretty easy. But the stuff drifted to the northwest and to the west and came down in all of these different countries that you see on this map. And a heavy fallout is serious. It contains things such as radioactive strontium. Strontium is very similar chemically to calcium. So when cows eat grass that is contaminated with strontium, they make milk that has radioactive strontium in it because it acts like calcium chemically. And there are other problems, but that's one that was well publicized. So this is a serious situation here. And of course, the Chernobyl area itself, all of this red area, is still too hot for human beings to even live there or to farm there. Other safety issues, a link between nuclear energy and nuclear weapons. The spent fuel from the conventional plant can be reprocessed and then can be used for fuel in a breeder reactor, or it can be processed to make fuel for nuclear weapons. Radioactive waste, 2 types. You've got low-level waste and you have high-level waste. And these data are getting a little bit old too. But when it says 104 reactors, remember that's not plants, but that's actual reactors. And that number is probably a little lower now. Other countries with high numbers include France, which gets, I think, about 70% of its electricity from nuclear power. Spent fuel inventories. Most of the spent fuel stays right at the nuclear power plant where it was produced. These numbers are metric tons of radioactive waste. And this is how some of that is now stored. They call them temporary storage, above ground casks, and these are moved all over the place sometimes on railroad flat cars or even semi tractor trailers. You can see that this thing is designed to contain spent fuel rods, and it's sealed up pretty well, but again, it's temporary, and these casks aren't expected to last forever. And some of the things inside have half-lives that are in terms of thousands of years. So now, because this waste is spread all over the country, there's been a desire on the part of the nuclear power industry, plus government regulation, to try to get it all into one safe place where they can bury it underground. And some of these places where they want to do this is like Yucca Mountain, Nevada. There is a site in Texas, way out west, close to the New Mexico border in Andrews County. Nearest town is Andrews. Both of these sites have been very controversial. NIMBY means not in my backyard. And the one in Andrews County has been fought tooth and nail by many environmental groups, including the Sierra Club. And there's another site we'll look at in a minute. Most of the waste generated by these power plants is still there. And this is over here on the left is a diagram of how these permanent storage sites are supposed to work. And again, we hope that none of this stuff leaks out, gets into the groundwater, and so on. Or that there's no disasters like huge earthquakes that let the material out in any form. Other considerations about nuclear waste. You have high-level radioactive liquid waste, short half-life, decommissioning nuclear power plants. This is one that has become a concern. Let's look at this map here. Where is radioactive waste now stored? Well, see, these black dots are operating commercial sites. Here's the South Texas project in Comanche Peak. They store their own stuff. All these black dots are operating nuclear power plants that store their own radioactive waste. Also notice these X's are plants that have been shut down for one reason or another, very often for safety reasons. There's quite a few of them, isn't there, scattered around the U.S. And these may become more important in the future. And I'll tell you why in a minute. Here are these proposed repositories that are supposed to be permanent. There's Yucca Mountain, which is northwest of Las Vegas, about, 140 miles. This one is in Andrews County, and I don't know exactly where this one is, or if they're storing anything there at all. But this is temporary, okay, and at this point, and so are these others at this point. But the industry and government, the Nuclear Regulatory Commission, would like to get this stuff away from all these sites that are spread all over our country into some safe place out in the middle of nowhere where there's not a lot of people that have any kind of political power to stop it. But which is why we are in Andrews County here, and why this one's here. This one is out in Nowheresville in Nevada. However, there are many environmental organizations that have stuck their nose into this business, like the Sierra Club, for example. All right, well, just briefly, fusion. Is fusion the nuclear energy for the future? Well, in a way, it's the future, it's the energy for now, isn't it? Because the sun is, the energy coming from our sun comes from fusion, okay? And so solar power is from fusion. And this involves the high pressures that can put two atoms together to make something new. Deuterium and tritium are isotopes of hydrogen. We know it's hydrogen because there's only one proton in both of them, and that says hydrogen. But there's differing number of neutrons, and that says isotope. Normal hydrogen has no protons. I meant no neutrons. Sorry, no neutrons. Normal hydrogen has one proton. Well, under the tremendous pressures and heat in the sun, what happens is these can be combined into a totally different element, in this case, helium. And what happens then is we have a free neutron come out and even more energy than we get from fission. This is what happens in a hydrogen bomb, okay, or a fusion bomb. A lot more energy than the old atomic or fission bomb. So it would behoove us to make better use of the sun itself, because containing a little sun here on Earth has proven to be very difficult, and it may not happen ever. And if it is going to happen, it's going to be quite a ways in the future, where we could contain a fusion reaction well enough, a sustained reaction, to actually generate heat and make electricity. What we've done so far lasts for like fractions of a second, you know? Okay, the future of nuclear power. What are the issues involved? Well, making it safer. We know that there are some safety issues. Standardizing power plant designs so that if something goes wrong, everybody that works in the industry will know what to do about it. If you have all kinds of different setups in engineering, then it creates a problem. Only a few people may know how the place works. And here, this is something very significant here. The Biden administration is launching a $6 billion effort to save nuclear power plants that are at risk of closing, citing the need to continue nuclear energy as a carbon-free source of power that helps to combat climate change. And of course, it also helps to prevent or to combat other forms of air pollution besides just CO2 and methane. Now, you remember the map that showed all of those closed down power plants, these red boxes with the X's? I think that a lot of these might be able to be brought back online through this $6 billion effort to produce more electricity. Is that good? In my opinion, it's something we need to do. Because if you remember the graph that showed future electricity generation, by the middle of the century, we still have a problem with natural gas being a primary producer of electricity. So in order to make our transition from fossil fuels, and that includes natural gas, to renewables, we're going to have to produce more electricity with nuclear power during that transition. And by the way, nuclear power is not renewable because uranium is a resource that is mined and it's not unlimited. So hopefully the nuclear power plants would be temporary as we make a complete shift from fossil fuels and nuclear to the renewables, solar, wind, hydroelectricity. There are many experimental designs going on with hydroelectric that do not involve big dams and things like using tidal flow to generate electricity and things that harness energy from the waves movement and so on. Okay, that's the end of my presentation. So if we have some questions, I can take a shot at them now.
Thank you so much, Dan. That was extremely informative. So yes, we do have a few questions. So let's get started so we can get through as many as we can. So first question, are there regulations on who can and can't produce nuclear energy?
Well, yeah, the Nuclear Regulatory Commission has to license a new power plant. You can't build a new power plant unless you get it licensed, and that's supposed to include engineering design and so on, meeting certain standards. So yes, there is regulation of the nuclear power industry.
As a follow-up to that, are there are there international regulations, or is that just within the US? Like, is there any way to control whether one country has it and another doesn't?
No, there's no way to any country that wanted to do nuclear that was capable of it, I believe, would be able to do so. I mean, an example is Chernobyl. The Russians built the plant. Chernobyl, by the way, is in the Ukraine, okay? And that plant was built with all kinds of technical and engineering flaws, which is what led to the meltdown and the explosion. So there is an International Energy Commission. How much control they have over who builds a nuclear power plant and does it have to meet certain standards, I really don't know. But I think it's pretty darn loose.
Sounds like it, yes. Where exactly, where in parts of the world is uranium found? Is it everywhere?
No, uranium's not everywhere. Australia is a major source of uranium. The United States produces a lot of uranium also here. And those are two major sources of uranium. And I'm having trouble. Okay, so like in the US, we have a uranium mined in Wyoming, Texas, Colorado, New Mexico, and Utah. Other countries that produce uranium are Australia, 20% of all known resources, Kazakhstan, which is a country that used to be in the Soviet Union, 18%, and the US has 10%, and Canada has 10% of all known uranium deposits. And Africa, basically South Africa, has about 9%. So that's where it is in the world. The uranium, which is U-235, that has to be refined and enriched to become it's U-238, which has to be refined to be U-235 to be used in a nuclear power plant.
Okay, okay.
Or a bomb, for that matter.
So, sorry, this is really interesting. Just to, so all of the nuclear power plants around the world, they get their uranium from one of these uranium mines, in the U.S., Canada, Australia, South Africa, all the countries you listed.
Yeah, pretty much so.
Interesting. Okay. Okay. Next question is, how likely is it that there will be another accident like Chernobyl and Three Mile Island? Is there progress being made in safety regulations to prevent it?
Well, I can't speak to the world as a whole, but I would think there were some lessons learned at Chernobyl in Ukraine and at Fukushima in Japan. And for us, 3 Mile Island, which came close to being a serious problem, that the industry did learn some lessons from that. And of course, in our country, those lessons will be applied to actually, not only to any new plants, but it's much more likely that old plants that are offline will be fixed up in terms of their safety, rehabilitated and renovated and so on, and bring them back online. And they should be safe. Now, I can't speak. I mean, who knows? I mean, you take a nation like Iran, where they're trying to refine a U-235 to amounts that are needed for a bomb. And I don't know, who, if anybody, is regulating what goes on there. There is an agency that goes and checks on them, the International Atomic Energy Commission, but they hide what they're doing. They don't take the inspectors to where they really should be going and so on. So it's hard to say what's going to happen in the future. But in our country, at least, I don't think we're going to see another problem like we saw at 3 Mile Island in the 70s. And certainly nothing like we saw at Chernobyl. And the problem at Fukushima was caused by a tidal wave swamping the plant, knocking out all their cooling systems, which were electrically driven and so on. And hopefully we wouldn't see that in the United States. Okay, that's about the best I can do with that one.
Thank you. Thank you. As a quick follow-up to that question, are those sites like Chernobyl and Fukushima, will they ever be habitable again, or is the damage permanent?
As far as human beings go, the damage is pretty much permanent. Now, Fukushima didn't cover as large an area as Chernobyl, but Chernobyl has put out of commission a tremendous amount of highly productive farmland. It's radioactive as heck. You can't farm there anymore because of the half-lives of some of those radioactive isotopes like plutonium. I mean, forget it. I mean, people will never be able to go back into those really hot areas. I think Fukushima did a better job of containing the radioactive waste leak, but they still have serious problems even now. And some of their waste leaked out into the ocean, and so they may be seeing problems with marine life, like Godzilla. You know what Godzilla is, right?
I think so. I haven't I've seen like the remake versions of it, but I'm pretty
Yeah.
sure I'm pretty sure he's like a product of like nuclear energy getting dumped in the ocean.
Yeah, that's right. Uh, it was a reaction to the use of atomic weapons on Japan. Um, okay, but the sites themselves, I mean, the reactor itself at Fukushima is they have to seal it, and you can't go in there. I mean, that's basically off limits for thousands of years. So I would say that the damage is permanent because of the half-lives of some of these radioactive isotopes that we're dealing with.
Thank you. Next question. So you mentioned cows slash strontium issues. What other issues were seen and how lasting were they? And how did each affected country deal with these issues?
Well, of course, Chernobyl led to all kinds of cancers in people, all kinds of cancers. And it was difficult to get information out of a country like Russia, but information has, since 86 has slowly been compiled, and many people, including lots of kids, have gotten various cancers. And how has Russia dealt with it? Probably not much at all. I mean, Russia's not a country that is good at dealing with problems that its people have, especially if they're not people with money. Now, Fukushima has a big testing program trying to see where the pollution has gotten to and if it's still spreading. Is it in the groundwater? See, that's another problem with this pollution, is if it gets into the groundwater, it may pollute aquifers where people will get their drinking water from. So we didn't have any big problem like that with 3 Mile Island because they stopped the meltdown before it occurred. So most of the release there was in the form of gas, which just blew off in the wind and didn't really cause any serious problems with people anyway that we're aware of. But I assume the Japanese and lots of people that have had to work, I mean, in these melted down plants have died from the exposure that they got. In addition to causing cancer, it also damages your DNA, the radiation. And of course, that is what causes a lot of cancers, the damaged DNA. Okay, I'm done with that one.
Thank you. Next question. And so there might be some more questions that come in, but we've got one more question. So other than energy and bombs, is nuclear energy used for anything else?
Sure, it's used in medicine. Radiation can be focused. Well, I don't know if you want to call that nuclear energy. It uses the breakdown of radioisotopes, which it does involve the nucleus, and it produces radiation that can be focused on tumors to kill them. That's what radiation therapy is when it comes to treating cancer. And other industrial processes, no, it's also utilized, of course, nuclear reactors can be utilized to power vessels such as submarines. We have nuclear submarines, we have nuclear warships, such as the giant aircraft carriers of today. They use nuclear reactors to produce electricity, and that drives big electric motors that propel the ships. That's all I could think of, really. So nuclear energy, some medicine uses, and to make energy to power vehicles, which requires small nuclear reactors.
Okay. So you can find you're talking about like chemotherapy and radiation for cancer treatment. So just can you clarify? So the same thing that might cause the cancer can treat it as well. How does that work?
First off, not chemotherapy, because that uses chemicals to try to kill the cancer cells. It doesn't involve any kind of radiation. Yes, when you do radiation treatment to treat a cancerous tumor, you are focusing the radiation to a little, to just hit the tumor, not the rest of your body. That radiation will kill those cells by disrupting its DNA or outright killing the cell in some other way. which is what happens if you get radiation poisoning and sickness. The difference is the dosage is just enough and focused to kill the tumor cells in your body, hopefully. Is it possible that it could cause damage to other cells that weren't the target? Yeah, it's possible. I don't know if we should call that nuclear energy or not. It utilizes the breakdown of radioactive isotopes that are producing radiation in the form of particles and other radiation, like perhaps gamma rays, which what X-rays are.
I see. Thank you. So there are good uses for nuclear energy. So
Well, right.
it's
And the
right,
production of electricity is the best use because we
right.
really need to get off our use of fossil fuel, coal, natural gas, and onto renewable things. And in the case, I've already said nuclear energy is not really renewable because uranium is a mined mineral, but it produces really no air pollution that would contribute to global warming, although it does produce radioactive waste products, as we discussed.
Thank you. One more question came in. So, is there any research being conducted to neutralize radioactivity in the waste products or contaminated lands?
Well, there isn't any way to treat radioactive waste products except to store it somehow. Now, if we could control fusion on this planet, in other words, create a small star in order to make electricity, we could feed a lot of our waste products into that small star and they would be completely broken down. But I don't think any of us are going to see that happen in our lifetimes. Although eventually I expect that it would. But there's no way to treat the stuff in order to make it not radioactive, except to let it break down in its own good time, which in some cases is thousands of years. Was there more to that question? I forgot.
No, no, I'll repeat it just in case. But the question was, is there any research being conducted to neutralize radioactivity in the waste products or contaminated lands? And I think you answered it. So really, not really, unless
Well, no, not
we're very
really.
far from it. Mhm. Okay. And how can we be sure, or are we sure that where we're storing the radioactive waste, are we sure it's not leaking, or is there no way to be sure?
Well, supposedly these casks are inspected. We looked at those casks that contain the old uh, fuel cells. They're supposedly inspected every week or so, looking for any cracks or anything else that might possibly corrosion and so on that might go wrong with them so that would be corrected. Yeah, hopefully before they began to leak. Uh, and the ones that are like Yucca Mountain is large salt deposits. So I don't think they would want to bury these things in the ground because then you can't inspect them anymore. They put them in these salt caverns where you can still go down in there and inspect the casks. But the worry, we're talking about isotopes that will take thousands of years to break down. I mean, longer than human civilization has been around. So during these time periods, is there a potential for earthquakes? Yeah. Is there a potential for other things to go wrong, such as possibly rising water tables, uh, asteroid strikes? I mean, once you create this stuff, you're basically stuck with babysitting it forever. And yeah, you have to inspect where the containers and the places where it's stored. And that, of course, is why we would like to eventually eliminate generating nuclear power too. But in the meantime, I think we're going to have to use it and possibly generate more electricity than we are now to make the transition to renewables, sun, wind, water.
Thank you. And I think that's a very good way to end this presentation. Thank you to the audience. Thank you, Dan. Is there anything else? Oh, if I think we do have time for one more question. We've got about 3 minutes left, and one just came in. So, is there any way to use the radioactivity um, uh, on the on the isotopes for any other purpose?
Other than the ones I've mentioned, you mean, I
Mhm.
guess? Well, I don't know. If there is, I don't know about them. But, uh, the problem with the radiation that's given off by radioisotopes is it's what's called ionizing radiation. That means and there's various different types of particles and rays. Alpha particles, for example, will not even penetrate your skin or a sheet of paper, so it's less dangerous. Beta particles will penetrate your flesh, and it can ionize your DNA. That could cause mutations, uh, and so on. Um, I don't know of any productive way uh, that we can use that radiation. But that's something you might want to research on your own.
Thank you. And I actually do have one more question. So, in the event of a nuclear plant exploding or a nuclear attack, is there anything to be done? Like, is there anything we can prepare for or do in that case?
Well, I guess you weren't alive during the 50s when everybody was building their bomb shelters. Because, back in the 50s, the mutually, ex, mu, the everybody, the Soviet Union and the U.S. had all kind of nuclear missiles pointed at each other. Mutually assured destruction, MAD. So, yeah, you can build a bomb shelter, such as the one the U.S. government built in the mountains in West Virginia under that famous resort, whose name escapes me at this minute. Uh, you have to shield yourself from the radiation. It's that simple. So you can do that by going underground or into caves. Now, if your food supplies and the soil that grows your food gets polluted with radioactive waste, then you have a problem. And I don't know what you would do there. I guess what the survivalists do nowadays is they store all kinds of freeze-dried and canned foods in their bomb shelter. Uh, in the case of the explosion that happened at Chernobyl, you see where that it's spread all over Europe and into Scandinavia. And there's very little you can do except possibly avoid certain products where something like strontium behaves chemically like calcium. So if it's in the cow's milk, it's going to get incorporated into your bones. And that's a bad place to have radioactivity in your bones, because your marrow is making red blood cells and so on. I don't know. That's the best I can do on that one.
Thank you so much. And yeah, I'm very familiar with what happened in the 50s. I wasn't alive back then, but I've seen it in movies and television. So yeah, thank you for answering that one. Thank you to it looks like we're out of time now. Thank you to the audience for joining us today. So thank you so much, Dan.